Hey, thanks for joining me. We're going to do two examples of questions using the z-distribution table. Turns out the second example isn't terrific, but you'll see the process at least as we go over this. So first of all, use technology. Oh, what does that mean? Use technology means that there are ways to find out the relationship between z-distribution and the percentages that are on our table. We have a table we're going to use using your computer or your scientific calculator. Now, I will admit, here I am, a highly qualified math teacher. I don't know how to do that. So if you know, come and tell me so then I can tell other people. But for now, we're going to use a table to get the data that we need, and that is in the course, and I'll put it on the recording so you can see what it looks like here. Okay, so here goes. Suppose ages of people who own their homes are normally distributed with a mean of 42 and a standard deviation of 3.2 years. Approximately 75% of the homeowners are older than what age? Okay, let's first of all just draw our normal distribution curve here, and we know that there's a line right in the middle. It's not very well in the middle, but it's good enough. That is the mean, which in this case is 42, and then we have these equally spaced lines that are equal distances apart, that we call that distance the standard deviation, and we can calculate what the standard deviation or what the data points are at one standard deviation above. That would be 45.2, and 2 standard deviations above, and 3, and so on. And we can do standard deviations below, right? So 42 minus 3.2 would be, I have no clue, 38.8, I think. 38.8. Okay, not using my calculator, you can tell. All right, so there's my chart, and then we said that there was percentages in here, and let me just, I have it on the next slide. There they are. There's the percentages. You got 34% on the one standard deviation away to the left and to the right, and so on and so forth. Okay, we'll go back to the problem. But none of the percentages are or add up to 75%. So here's the question that we're asking. Let's see if this makes sense. We're asking, if I draw a line here, I'm going to draw, there's a line I can draw somewhere, and I don't know where it is, but let's just say there's a line that I can draw here where, I'm just going to draw it like this, but I don't know, I'm just making that up. There's a line that I can draw here where 75% of all the data points, all the people described in this data, are above that number. Now, if 75% of the homeowners are older than this age, and I don't know what it is, it might be 40, it might be 39, I don't know, then if 75% of the homeowners studied in this test were older than that number, then how many were younger? Right? As long as anytime we draw a line that's pointing to a particular data point on this distribution, it cuts the data into two pieces, right? Two pieces that add up to 100%. So if to the right of that line is 75% of the people, to the left of the line would be 25% of the people. Okay. Now, here's the deal. Our z-distribution table, which we're about to look at, doesn't talk about how many or what percent are greater than a given number, and we're going to talk about what the numbers mean and what we call them. Our z-distribution table only tells us what percent are less than a given number. So when we use the z-distribution table, we're going to be figuring out how much or what percent is in the area below our number. We'll talk about what that means in just a minute. Okay, so that shaded region. But so I'm going to have to use the number 25%, even though the question said 75%, because it was asking about 75% of the people who are older, and if 75% are older, then at that exact same point 25% are younger, and the Z distribution table doesn't tell us about older, it only tells us about the younger. Okay, so that's what we're going to use for our Z distribution table. We're going to use the number 25%. Now let's talk about the number that gets matched up there. The number that gets matched up there is it's a number that points to this data point. Okay, so let's just say that this is 39. The age is 39. I just made that up. It may or may not be true. Let's just say that this is age is 39. What's the relationship between that number 39 and the data in this distribution? Well, the number 39 is some distance below the mean. What distance is that? Well, how do we measure that distance? Well, we could just subtract them and say it's 3 years below, but that's not standard. This is a standard distribution, a normal distribution. Instead, we use a measurement called a standard deviation. Okay, a standard deviation, and so we say 1 standard deviation below the mean is 3.2 years below, which is 38.8. But how do we measure if it's not a whole standard deviation? Well, we can measure it in partial standard deviations, and the name we have for that number is the z-score. So the z-score is how many standard deviations away, and it's if it's to the left, it would be a negative, right? So negative standard deviation. Negative z-score means you're moving so many standard deviations away to the left, and a positive z-score means you're moving so many standard deviations away to the right. And the z-score oftentimes is going to be a decimal because it's a fraction of standard deviation. So it might be 1.5, which means 1.5 standard deviations, or it might be a 2.1, which means 2 and a little bit more of a standard deviation. Okay, so that's, now the z-score is, surprise, surprise, what we find on our z distribution table. And the z distribution table matches up the z-score, which is distance from the mean in standard deviations, with the percent of the distribution, the percent below that point on the data, so below that z-score data point on the table. So sometimes we refer to this as the percent. What percent of the data is below that line? Sometimes we refer to this as the area, because remember, this is a continuous probability distribution, and sometimes we refer to this as percentile. And so that's not what the language that was used here, but it all means the same thing. It means this number refers to, or this area is what percent is below this particular number, which is associated with the z-score of a distance, a measurement of the distance from the mean. Okay. Oh, that was so complicated. I'm so sorry. Let's go into brass tacks here. The question said 75% are older than what age? Okay, so we're trying to find the age here. But our z distribution table only deals with the amounts less than, so we're going to turn that around and say, well, that means 25% are younger. So what z-score is associated with a 25%? So let's pull up our chart. Woohoo, there it is. Hopefully you can see this. There's our chart. And so we have a column on the left, that's the z-score column, and then the row on the top is the hundredths place. So we can calculate z-scores to the hundredths place using this chart. So it's a pretty involved chart. And we're looking for 25%. So you can see that all the rest of the boxes are filled up with decimals that could be written as percent. So for example, I just highlighted 82.89%. Okay, It's 0.8289. We're looking for 25%, so it looks like I'm going to need to scroll up quite a ways. This chart is in the course, and you should definitely put it in your notes, or at least save it to your desktop. Okay, so we're looking for 25%. There's 23%. There's 24. Then to the next line we go, oh, there's 25%. Now here's the thing. We don't have exactly 25%. We have 25 in 1400%, right? 25.14%. And we have 24.83%. Now, 25.14% is 1400ths above 25%. 24.83 is that's 1700ths below, right? It's 0.0017 below 25%. This is 0.0014 above 25%. So we're going to go with one that's closest. So I'm going to go with this one. And then we're going to look across to negative, to the z-score for that percent is negative 0.6, which is what we expected, right? Negative number. And then we have to scan up from there to get the hundreds, so it's negative 0.67 from the top column. Okay, so there's my z-score. Let's go back into, so negative 0.67. So my z-score then for this percent, the associated z-score is negative 0.67. I should have said 0.67, but that's okay. You'll get the idea. Okay, there's the z-score. And so then we want to know what number is that far away from the mean. Z-score negative 6.67 means it's a little bit more than half of a standard deviation away to the left, right? The negative means going down, and it's 0.67 is a little bit more than half. So we're gonna, this is easy, this is how we do it. The formula is you take your z-score, you multiply it by your standard deviation. This is a Greek letter whose name I don't know, something like this, but that stands for standard deviation, plus your mean, and there's supposed to be a Greek letter there, but I can't remember what it looks like. Okay, so z-score times the standard deviation plus the mean equals the number that is that many z-score away from the mean. So z-score is negative 0.67, standard deviation is 3.2, and plus the mean, which is 42, and we'll get our answer. We'll pull up our calculator. We'll try to do this very, very fast. 0.67, make it negative, it's negative 0.67, so I hit the plus minus button, times 3.2 plus 42, so it's actually 42 plus negative 2.144, so it's going to be subtracted. So plus 42 equals, and it's 39.856, which is actually really close to what I guessed. No, I said 39. That's okay. So the answer is 39 point, what did I say, 896? We're going to round this to the same level as the data we had. So our standard deviation was 3.2, and so I'm going to round this to the tenths place. So 39.856 rounds to 39.9. It might be more appropriate to say 40 years, rounding it a little bit further, but it just depends on the context, and oftentimes it will tell you what decimal place to round your answer to. Okay, there's that. That's how you do the z-score distribution table to figure out percentages below. And again, 25% of people were younger than 39.9 years old, and that means 75%, all the rest, were older than 39.9 years. So that's why this is the right answer, even though I didn't actually use the number 75 most of the time. Okay, let's go back to this one. Use technology, find the indicated area. The odometer reading, a random sample of identical model of sports cars are normally distributed with a mean of 120,000 miles, a standard deviation of 30,000 miles. Consider this group of 6,000 sports cars. Approximately how many sports cars will have less than 150,000 miles on the odometer? Okay, so here's the funny thing about this example. This example actually we could have answered several units ago. This is 1.13, less than 1.13, but we could have answered this 4 or 5 lessons ago when we first were introduced to this chart here, because, and here let me show you why, because if we do our standard, our normal distribution, the mean is 120,000. The one standard deviation above, because standard deviation is 30, would be 150,000. One below would be 90,000. And looky there, 150,000 is what we're being asked about. So from our chart, we can see that this area right here is 34%, plus the other half. Remember, this median line cuts in half, so the other half is 50%, so the whole thing over on the left side past the median is 50%. So the area, total area here is going to be 50 plus 34, or 84%. So 84% of the data, 84% of the cars are going to be less than 150,000 miles on the odometer, and 84% of 6,000 sports cars of 6,000, that's a multiplication problem. We just multiply 84% 0.84 times 6,000, and we get 5,040 equals 5,040 sports cars. Okay, so there's the answer, and that was with this original information, these percentages that we have here on the right-hand side of the screen. That would have been great, but let's do this again, but this time with our distribution table. So we're going to take we're going to find the z-score first, because that's we wanted to find what the percentage is. I got it by adding up the percentages, but I want to find it using the table now. So I need the z-score. Remember, to find the z-score, you're going to take the raw score minus the median divided by the standard deviation. That's how you get the z-score. That's z equals. Okay, so the raw score was 150,000 minus the median, which is 120,000, divided by the standard deviation, which is 30,000. And it turns out 150 minus 120 is 30, divided by 30 is 1. So the standard deviation is 1. So, whoops, wrong button. We'll do the standard deviation of 1. So scroll down to standard deviation of 1. Z-score of 1, that's 1.0. That would be right here. And there it is. The percentage is not 84%, which is what we said it was from our rougher data. It's 84.13%. So that's interesting that if we use the z distribution table, we get 84.13% of 6,000. And if I do the math, it comes out to about 5,047. I won't do that on the calculator. But so this is the difference between this original kind of breakdown of the percentages, which is pretty accurate, and the z-score table, which I'm hoping is a little bit more accurate, and that's something to be kind of aware of. All right, but at least you got to see the process of using the z distribution table by first finding the z-score and then looking it up and finding the percentages. And thank you very much for watching. I hope this helped.